Welcome to this presentation in the series, Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am your narrator, David Beams, Associate Professor Emeritus of Electrical Engineering. And in this short presentation, I want to address the subject of using the One Human Lifetime Project resources for filters to design a Butterworth high-pass filter. The questions that we will take up in this presentation are, well, how do we use these design resources to design a Butterworth high-pass filter? What's the process? Secondly, how do we simulate the filter with LTSpice and verify its performance? Third, since the Salon Key design worksheet that are part of the One Human Lifetime Project filter resources is for designing second order sections, how do I design a first order section if my design specification calls for an odd order filter? See, as you might guess then, I am planning for an odd order for this prototype. To illustrate the design process, we're going to do a third order filter requiring a first order section and a second order section. I'm going to specify that the filter have a high frequency gain of unity or 0 decibels. The pass band will define the end of the pass band where the gain drops by -3 decibels. And since this is a high pass filter, the end of the pass band will be at the low end of the pass band. The pass band will extend above this -3 dB frequency. And let's set it at 500 hertz. First step is we find the characteristic polynomial of a third order Butterworth filter from the resource of the Butterworth polynomial tutorial. And rather than make you look it up, I've reproduced it here. This is the characteristic polynomial for a third order Butterworth filter. It consists of a first order term, which, as you might imagine, is linked to a first order filter section, and the second order term linked to the second order filter section. Okay, just for context, what the characteristic polynomial is taken from is the transfer function of a third order high pass filter. And here we have the transfer function of high pass function of the first order section. Here we have the transfer function of the high pass second order section. We will need the coefficient of the linear term, that is s to the first power, from the denominator of the second order term that we will need for the Salon Key design worksheet. Now, just for context, the coefficient of the linear term in S here is omega naught, which is the pole radius or undamped natural frequency of the poles. It's omega naught divided by the quality factor of the poles. In this case, since we're designing a filter with a pole radius of 1 radian per second, omega naught is 1. The coefficient of the linear term of S here is 1, which gives us a Q of 1. Okay. The design process is identical to the process that was used in the design of a low-pass filter. First thing we do is we find component values of a prototype filter with omega naught of 1 radian per second and with a Q equal to 1 over the coefficient of the linear term of the second order denominator. Okay. The second step is to scale the capacitors to change the value of omega naught to the design value. The third step is to scale the capacitors again to change them to realistic practical values. And then we scale the resistors by the inverse of that second capacitor scaling factor. And If it turns out the resistor values are impractical, we can change the capacitors and try again. But all of these steps are built into the spreadsheet. So I'll tell you what, let's first take up the topic of design of the first order section. How do you design a first order high pass section as part of a odd order high pass filter? This is the topology. We have an RC network, and I have a buffer amplifier here that just simply isolates this RC network from any circuits downstream of it. And for a pole radius of 500 hertz, or 2 pi times 500 hertz, pedantic, because this is actually in radians per second, 2 pi times 500 hertz, I need a time constant of 318.3 microseconds. Oop, oh, I've gone too far. All right. Let's now go to the spreadsheet. And we will design the second order section. All right, here is the second order section. This is the high pass tab of the Sallen-Key filter design worksheet. It looks very similar to the low pass tab. It's no accident, they are very similar. The boxes in yellow, the cells that are in yellow, are user entered values. Component values that are produced by the spreadsheet are these boxes or these cells that are filled in with a light blue background. And you'll notice here that 3 of the 4 component elements, the 3 of the 4 passive components, have yellow backfill in their cells, indicating those are user entered values. The 4th one is not. Reason for that, the product of C1, C4, R2, C6 is going to be 1 for 1 radian per second. And if I choose 3 out of the 4, the 4th one is determined. So I chose to make R2 the value that's calculated from the other 3 values. So don't change the value of this cell. As a matter of fact, there's a formula there. Don't overwrite it. The value of the voltage amplifier in the Sallen-Key circuit is, its gain is here. And this is the coefficient of S in the second order denominator. And with the component values, you see here it's 1.414, but we know from that third order polynomial that the coefficient we want, the design value is 1. Let's change that. Now, here in this cell is the computed value of the linear term, in the coefficient of the linear term. And our design task will be to vary ours to make this value identical to, or as close as possible to, the design value. We'll do that by changing R6. We're going to leave the capacitors fixed, change R6, which of course will also change R2 in the process, and see if we can find a combination that reduces the computed value of the linear coefficient to the design value. So let's, we can try it manually by changing R6. Let's see if I change it to 1.5. That's a better guess. Let's try 1.8. Seems to be doing better. Squared error term. This is the square of the difference between these two numbers. The squared error is getting smaller. Let's try 2. Whoa, we got lucky. Didn't need solver here, although we could have used it. Looks like we've got it. We've got a solution. Okay, So now let's move over here to scaling it for the actual pole radius. We want the cutoff frequency to be 500 hertz, and I've already apparently had entered that, 500 hertz. So that step's done. Now, I chose as a practical value for capacitor C1, 10 nanofarads. That's a readily available standard value. And since we initially had equal values for C1 and C4, then the final value of C4 is equal to the final value of C1, or 10 nanofarads. And that produces R2 of 15.9 K and R6 of 63.7 K. So now we have our design. Let's put it in LTSpice and see how well it performs. Here's the design in LTSpice. In this first order section, I chose a standard capacitor value of 47 nanofarads, or 0.047 microfarads, and that, to give a time constant of 318 microseconds, required a resistance of 6.77 K. So let's run this and see how it performs. Let's maximize just the graphical display window. Let's add a trace. Now, I had labeled the output of this high-pass filter as node VB2. So the voltage at VB2, so I want to look at. And you notice that the response is at high frequencies is uniform and is 0 decibels, what we wanted. And it certainly appears to be a maximally flat response. Does it meet our 3 dB at 500 hertz criterion? It's a little difficult to see with this scaling. Let's see, 200, 300, 400, 500. There's 500. And it's, well, I tell you what, let's expand the scales so we can get a better idea of where it actually crosses -3 decibels. Let's change the magnitude scale so that we have increments of 3 decibels. And let's say it goes to -24. All right. Now, the solid line here, by the way, is the magnitude response in decibels. This little dashed line here is the phase response of the network. Okay, and I'm going to say, let's say we start the frequency scale at 10 hertz. Now let's put a cursor on it and move until we are at 3 decibels. It's a little touchy. There, I think that's pretty good. Look at that. Oh my, look at that. At 3 decibels down, the frequency is 500 hertz. I think we've nailed this design. Okay, but now you may be asking, what happens if we substitute standard resistor values for the exact resistor values that I used in the prototype? So let's go back to the original design and let's substitute for the actual resistor values. Let's substitute the closest 5% tolerance values available and just see how much it changes the performance of the filter. Here's the filter with resistor values replaced by their nearest 5% tolerance standard values. 6.77 K, the exact value, was replaced by 6.8 K. 15.9 K was replaced by a standard value of 16 K. and 63.7K was replaced by a standard value of 62K. Let's run it. And maximize plot settings, add trace VB2. It certainly looks pretty much like it did before. There's not a whole lot of difference. I mean, we could make fine measurements and find small differences, but it looks pretty much like our design specification. So I'll tell you what, let's home in on let's do the same changes in the scales so that we can get a better reading of where it crosses -3 decibels. And okay, here's 100 hertz, 200, 300, 400, 500. And there's -3 decibels. It's moved a little, but not much. Let's see. Let's try putting a cursor on it and see if we can quantify how much the -3 dB frequency has moved. And my reading here, we're at -3.01 decibels at 508 hertz. A minuscule change in the -3 dB frequency. So I would say that this is a perfectly acceptable, practical solution to meet our design specifications. So let's wrap this presentation up. Remember, the link to the filter resources of the One Human Lifetime Project will be in the video description. And if you find these resources useful, leave a comment, let us know. We always appreciate hearing from you. So until next time, we appreciate your visiting with us. Keep those cards and letters coming. And I thank you for your time and your attention, and see you soon in another video from the One Human Lifetime Project.